All right, this was going to go out to Jenny and Katie. They're not here today. So we'll send you watch. I told you to watch the videos. They're up now. Okay. Bailey's laughing at you. So is Nikki. All right. This is back to the real science, real chemistry here. We did a little detour off on global warming and climate change. Why did I do that in this chapter? Well, it's simple. It's we're talking about carbon. We're talking about carbon dioxide. We're talking about organic chemistry, and it fits right in with that. All right. By the way, I should mention this. Don't all the stuff I'm telling you, all the skeptic stuff that I've given you, the anti-global warming stuff. Don't ever dare to tell a professor at college and stuff. You tell them whatever they want to hear, because they'll take off points. They will kill you. I've seen it happen. I've absolutely seen it happen with kids coming back to me with papers, and they wrote something that you tell them whatever they want, they hear, because otherwise, unless you don't care about getting a grade, you want to fight somebody, but you're not going to win because these guys got tenure. But trust me, what I said was the equivalent of heresy. What you've heard was the equivalent of sacrilege. Back in the Middle Ages, and you'd be put on a rack. And the equivalent of the rack is you'll fail, or they'll give you a very bad grade, all right, for saying the kind of stuff that I said. What I told you about the science is all everybody agrees with: the greenhouse effect, how it works, long wave radiation being trapped, short wave coming through, all that stuff. But if you were dare to say that, we're not all going to fry in 30 years, and you're just Hitler. You're a Holocaust denier if you don't believe in global warming. So just to make that clear, do not repeat this to your professors, or they will punish you. It's as simple as that. Okay, and I've seen it. I'm not saying this without absolute certainty. I've seen it myself with kids coming back to me and telling me this. I think it's the truth. And again, what I've said, I think hopefully you got this from this. Hopefully you got it from the previous one. I am not saying I'm 100% right. They are. They're saying the debate is over, we're right, you're wrong, go home. We have the ball. That's what they're saying. I'm saying, I don't think it's that bad. I think they've made predictions in the past that haven't come true, and I think what they're saying, from all the stuff I gave you, is exaggerated. At the very least, is exaggerated. And we should be careful how, I like a clean environment, and I want to do things for it, but I think we should take a cautious approach. No, that's not good enough. Anything against it is like saying you don't believe the Holocaust actually happened. That's what you are. All right, let's get back to chemistry, though, now. All right, turns out that we're going to be doing a lot with polarity. I want to do a little preliminary review kind of stuff here we did from Chem 1, because tomorrow we're going to go beyond this. But just to keep, just to refresh your memory about what polarity was. Polarity is a separation of charge across a molecule. Turns out that is very important when it comes to organic molecules. And we're going to talk about that today and for the next 3 days. We're going to do a little lab on it. We're going to have a model lab. Kate Upton's going to come in, Heidi Klum, and we're going to do a model lab. Not those kind of models. Ethan. Wrong kind of models. Actually, it's going to be Chippendales. So the girls will be happy. No. Different kind of models, little sticks and balls we'll be putting together, and trying to show you how these things fit together. All right, so describe the separation of charge across the molecule. And it depends, as you remember, on electronegativity difference. You remember what those differences were? What was the difference we were looking for? What were the cutoff points I gave you? Do you remember? 0 to 0.4, right? 0.4 to 1.7, and 1.7 or above was ionic. Remember that? Well, I'm going to write them all back down here so you have them, and I'll give you, a little bit of practice on some very simple ones. We're going to go beyond this year, much further than what we saw for those back in the Chem 1 stuff. All right, so let's go over those 3 classes for bond polarity, and we'll do an example of each, and I'm going to give you your electronegativity sheets as well. All First of all, we've got nonpolar, and as you said, the electronegativity difference is 0 to 0.4. Now, I think I said this last year as well. That is the cutoff we're going to use to do our actual calculations. In reality, there's no absolute cutoff, 100% perfect cutoff. Such that, like things that are around 0.36 or 0.42, they may be slightly polar or slightly more non-polar than polar. Same thing's true when you get to the polar ones. If they're right at 1.8 or 1.7 or 1.6 or 1.5, they might be considered ionic. Potassium bromide, for example, is, and it's below 1.7. It might be considered polar, depending. It's just a cutoff point that we're going to use, and our answers are going to depend on where they fall for that. That's all I care about. And, of course, ionic is above 1.7. Here they are. I was looking for your electronegativity sheets. Now, you got these sheets. I'm going to give them to you right now. And we'll do a couple of examples on the board, and I'll be done, all right, for today. That's all we did in Chem 1. That's all you had to do. I'll show you a couple of mistakes you might make. All right, I'll do a couple of examples, but you need these to do it. And, of course, these are electronegativity charts. They're also online. I'm going to show you that if I have time today. So. I'm giving an extra one here. Just steal one on the way back there. Walk back too far. I'm getting lazy in my own bed. All right. So, for some examples, I want to give you. That are going to show, hopefully, your mistakes you might make. Let's see. Find my papers. Here we go. So let's start with under examples. Wow, I'm going to have to redo this board. It's the best. Let's hope this is better. Well, no, this that was dumb. Wow, okay. Interesting. There. Why would it do that? I never clicked on that. Ever. Anyway. So these are under examples, and it's still not perfect, but HCl will be my first example. That's awfully easy, HCl. What would you do to get HCl? What would the difference be between these guys? Look up H, look up Cl, subtract them, what do you get? 0.8. Okay, so you get 0.80. Right? You see why? Everybody see why? Okay? That makes him what? Polar covalent. And we can abbreviate. You're going to have to abbreviate for some of your lab stuff you're going to do. Okay? Because it's very small spaces. Okay. That's an easy one. Now let's take a guy like this. What about Cl2? What are you going to do there? This is a diatomic element. We know about him. We know about those kind of guys. They're, there's Brinkelhoff, right? So, Cl2. What's the difference between Cl and Cl? 0. What kind of a bond would it be then? Non-polar covalent. Let's remember what polarity really means. Polar means who's pulling electrons, one way or the other. In the case of a non-polar compound, I've got two guys who have equal polarities. They're going to be pulling identically. Okay, so you're not going to actually have electrons spending more time around one guy than around the other. So there's going to be no charge. Non-polar. Poles. Poles of a magnet. Poles of the Earth. Charged. Positive and negative. Okay? You're not going to have that for a guy like that. In HCl, I had a minute ago, and I would have drawn a guy like this. Chlorine's pulling harder. You remember we used to draw an arrow for that? Remember? Okay? And it was slightly positive on that side, slightly negative on this side. Okay? All right, and let's do it. So we have that. We have diatomic ones. What do you do with those? How about another one? Let's try a guy like CCl4. And I want to know what the bonds are. And I'm using this guy for a reason. It's going to turn out later on in this week, we're going to find that our actual answer is completely opposite to what we're going to get right now. But right now, what do I do to get C and Cl4? I just take the difference between C and Cl. What is it? C and Cl's difference? 0.44, which is slightly above nonpolar, which makes him what? Polar covalent. However, what we're going to find, this is where I'm going to hint ahead to tomorrow's class and the next one, turns out that you can have guys like this who have polar bonds, yet the molecule itself is not polar. It's actually nonpolar. It has nothing to do with how big the polar bond is. It has something to do with the shape. And let's learn about that tomorrow. All right. And finally, one more example, CaF2. You won't see many like this. All right, but the key reason I'm giving you guys who have subscripts here, a guy like this, calcium fluoride, you don't multiply by the subscripts. You don't multiply the electronegativity of fluorine by 2. It's just the Ca and the F. You look them up. What's the difference between them? 2.98, which obviously makes him what? Ionic. All right, now a guy who's ionic like that, you're not going to see as many of them in organic, because most of the compounds we're going to deal with have all of them have carbon in them, right? And carbon's right smack dab in the middle of the periodic table. And that because of that, his electronegativity is kind of in the middle of all the other ones. So in order to get an ionic bond, you got to get a guy two guys who are different. One guy who's very electronegative and one guy who's not. All right, so one's pulling electrons closer to him, all right, than the other one. To get it actually rips them away. Actually, spends all their time rather for ionic, I should say. So you're not going to see as many ionic. Now that's a summary of what we did in Chem 1. Tomorrow we're going to apply this to something else, but I'm going to give you a paper that you can do a little bit of preliminary homework on, and that's this paper right here. There it is. You can do a little bit of preliminary homework on here. You're going to fill in the... Nope, that's not it. Wrong one. No, I had it. Oh, yeah, there it is. It's right in the same pile. You're going to fill in just in the bottom of these. You see this here? I just want you to tell me electronegativity difference, polar or nonpolar, for this section right here only. That's all you got to do. Same thing I just did there. It'll take you about 5 minutes, maybe at the most. You can probably do that before the bell rings if you wanted to. But either way, we are going to do these by tomorrow or the next day. So you want to get them done. Extra one in there.